All right, let's dive into a bit of a chemical mystery today. We're opening up a case file on some of the most common substances all around us. Acids, bases, and salts. We're going to go on a little investigation to uncover their hidden properties.
You know, we all know that lemons are sour, right? That's the acid. And maybe you've accidentally tasted baking soda. It's bitter. That's the base. But here's the thing. In a lab, tasting an unknown chemical is the absolute #1 thing you never, ever do. It's just way too dangerous. So the real question is, how do we figure out what's what without using our sense of taste? That's the puzzle we're going to solve.
So, think of yourself as a chemical detective. Our lab is the crime scene, and these unknown solutions are our main suspects. Our mission, should we choose to accept it, is to figure out their true identity. Are they an acid or a base, using nothing but some clever chemical clues?
Okay, so every good detective needs a starting point, and our first piece of evidence is all about color. We're going to use some special substances that act kind of like secret agents. They change color to reveal the real nature of our chemical suspects.
You've probably already seen this clue in real life without even realizing it. Think about a curry stain on a white shirt. The turmeric in the curry is actually a natural detective. The moment you scrub it with soap, which is a base, that yellow stain turns reddish-brown. This is our very first hint that some things give us a visual signal when they meet an acid or a base.
And that's exactly what an indicator is. It's just a substance that gives us a clear sign, usually a color change, when it's in an acid or a base. Litmus paper is probably the most famous one from school. But as we just saw, even stuff from your kitchen spice rack can do the job.
Okay, let's look at the evidence log here. This table shows us the unique fingerprints our suspects leave behind. See the acid? It does nothing to red litmus, but it turns blue litmus paper red. Now look at the base. It does the complete opposite, turning red litmus blue. And then there's our third indicator, phenolphthalein. It stays totally clear in an acid, but turns this amazing bright pink in a base. It's a really clear-cut way to identify them.
But you know, the clues don't just stop at what we can see. Some indicators actually work with your sense of smell. They're called olfactory indicators. Things like onion or vanilla extract, for example. Their strong smells pretty much disappear if you add a base, but they stick around just fine with an acid. It's just another cool tool for our detective kit.
All right, we've gathered our first round of evidence. Now it's time to turn up the heat a little bit. We're going to see how our suspects react when they're put under pressure, specifically when we mix them with metals. This next test is really going to help us build our case.
So what we're looking at here is a classic interrogation technique. We've dropped some zinc metal into our acid. And look closely. You see all those bubbles fizzing up like crazy? That's a gas being produced, and that's a very strong reaction. It's a huge piece of evidence. The big question is, what exactly is that gas?
And here it is, the big reveal, the moment of truth. When you bring a burning flame near that gas, you get a very distinct pop. That sound, that's the unmistakable signature of hydrogen gas. There's no doubt about it. Case closed on that gas's identity.
So this experiment leads us to a really important rule we can add to our case file. Whenever an acid reacts with a metal, you always get two things: a salt and that hydrogen gas that gives us the telltale pop. This is a core behavior of acids. The interrogation isn't over yet, though. We've got a new line of questioning. What happens when our acid meets something like a metal carbonate? Think baking soda or chalk. This is going to show us a whole different side of its chemical personality.
In this setup, we're reacting our acid with sodium carbonate. And yep, you guessed it, a gas is being produced again. But is it hydrogen? Well, to find out, we're going to bubble that gas through a special liquid called lime water. This is the one test that will give us a positive ID.
And there it is. That's our clue. As the gas bubbles through, the lime water, which was totally clear, turns all cloudy and milky. And that milky reaction, it's a positive ID for one gas and one gas only, carbon dioxide. Another suspect identified.
So this gives us our second major rule for the case file. When an acid reacts with a metal carbonate or a hydrogen carbonate, you always get three things: a salt, water, and that carbon dioxide gas we just identified.
And now it's time for the final showdown. We've seen how acids react with other things, but what happens when we put our two main suspects, an acid and a base, directly against each other in the same test tube?
Let's walk through this together. First, we take our base, and we add a few drops of that phenolphthalein indicator, which, as we know, turns it bright pink. Then, very slowly, drop by drop, we start adding the acid. As the acid begins to cancel out the base, you just watch, and poof, the pink color completely disappears.
This is what's called a neutralization reaction. It's beautiful, really. The acid and the base have totally canceled each other out. Their special properties are gone. And what are we left with? Just two completely neutral, harmless things, a salt and plain old water. It's a perfectly balanced conclusion.
So, let's close the case file. Our investigation has been a success. We figured out the core identities of acids and bases. We know they change indicator colors in opposite ways. We proved that acids react with metals to make hydrogen, and with carbonates to make carbon dioxide. And, most importantly, we saw that when they meet, they neutralize each other to form simple salt and water. Mystery solved.
But this whole investigation leaves us with one last really big question. We just proved that acids and bases react to create salt and water. Now think about that on a giant planetary scale. For millions of years, acidic rain has been falling on basic rocks all over the Earth. Could that simple chemical reaction, happening over and over, be the very reason our oceans are salty? It's a pretty amazing thought.
If you had fun cracking this chemical case with me and you want to investigate more Class 10 science concepts, you should definitely head over to the A1 Institute on YouTube. They have some fantastic tutorials and deep dives that really break down these complex topics and help you master them. Make sure you subscribe to their channel, and thanks for joining the investigation today.